And so let me define a few constants here for you. So E, which unfortunately is you guys might confuse with the exponential number, Euler's number E, but it's not here. E is what's called the fundamental charge, or the elementary charge of the electron. And it's exactly 1.60217663 times 10 to the minus 19 coulombs. All right, or C, as we call it. Right, so every electron and every proton contributes a fixed amount of charge. It's kind of the fundamental unit of one, what you could say in terms, when you put it in SI units, if you will. If you take the -1, which is an atomic number, it says that an electron has -1 charge. That's in atomic units. In SI units, this means that its charge is exactly this number, minus this number. Okay, so this is the fundamental. This is what in SI units a -1 charge means. That it has 1.6 times 10 to the minus 19 coulombs. Right? And of course, the amount of charge, the amount of coulombs a charge has, tells you how strongly it attracts to other charges. Right? The more charge a particle has, the more strongly it attracts things of opposite charge, and more strongly repels things of negative, of opposites, same charge rather. Right? So an electron has a fixed amount of charge, right, as it should. And protons have the same amount of charge, just opposite. Right? So a proton has plus 1.6 coulomb times 10 to the minus 19 coulombs of charge, and an electron has a minus 19. Okay, so the net charge, the net attraction, or the net kind of electrostatic interaction between the two electrons at a fixed distance is proportional to their charge squared. And then we have this 4 pi epsilon naught at the bottom. This is a strange unit, or a strange constant, but a very important one. And it's one of those numbers you don't really have to think about too much. Just know that it's there and it has a value. Right, this is what's called the permittivity of the vacuum. So the way to interpret this number, and I'll write it down, the units in a second. There are lots of different ways to write the units for this number. Because it's a number, let me find it really quickly. Hold on. Why is this not working? Where did my mouse? Oh, there it goes. Where did my mouse go? Okay, so this is 8.8541878 times 10 to the minus 12 farads per meter. Now, farad is a weird electrostatic unit. This is coulombs per volt per meter. So same thing. Okay, so what does this mean? So what is this number? So this is what's called the permittivity vacuum. So if you think about your flowing charge through a material, all right, so you have a negative charge here, and you have a positive charge here, separated through space. They have some attraction to each other. But the charge, right, the energy, which is you can think of electrons flowing, however you want to think about charge moving, it's an electric field, it has to propagate through the medium between the two charges, right? And the air or the vacuum that you're in, the material that it passes through, which is called a dielectric, has some sort of resistance, right? It doesn't freely allow you to move charge through. There's some resistance associated with the material, right? For instance, water has a very low dielectric constant because pure water is not very conductive. But when you put salts inside of that water, it becomes very conductive. So what that means is there's not a lot of resistance to motion of charge through the medium. So epsilon naught is what measures this permittivity, if you will, or the resistance, if you will, of the material in between the charges. And so what's the material between the electron and the proton and an atom? Well, it's just the vacuum, just free space. There's nothing in it. And free space has a resistance. Right? It's hard, you can imagine that, it's very hard to transmit charge across the vacuum. Maybe you've never tested this before, but it's not that hard to test when you have two electrodes in a vacuum. you have to really, really crank up the voltage to get a current across them because there's some resistance, right? It's hard to have that electric field or those electrons move from an anode to a cathode through the vacuum. It's not very conductive. And so the value that determines that conductivity, that resistance of the material, is epsilon naught. Right? And so every material is typically its dielectric constant, which is how easy it is to move charge through the material, is always referenced relative to this number. And so, for instance, I don't know the exact numbers, but it's very hard to get charge to move through a material. Right? It's hard to move coulombs of charge across a distance 1 meter at a potential difference of 1 volt. That's what this says, right? This says that if you're at 1 volt, if your electrode and your anode and your cathode are set to 1 volt potential difference, then the amount of coulomb, the amount of charge that moves through 1 meter of distance between the two is 8.8 times 10 to the minus 12 coulombs. Right? And so that says that actually, because there are 10 to the minus 19 coulombs per electron, this tells me exactly how many electrons are moving through the system as a function of time, given a distance of a meter between my anode and my cathode at a given voltage, 1 volt. Okay, so this tells you basically how readily electrons will move or charge will move between an anode and a cathode. In this case, the anode and the cathode are the proton and the electron. It's how easy it is to transfer electrical energy from a plus to a minus or vice versa. And so we need to account for that because vacuum is different than air, and the air is different than water, and water is different than a metal, right? Different conductivity. Some are insulators, some are conductors, and they all have different permittivities or dielectrics. Okay. So what this tells me now, now let's work this all together. The potential energy of two charges, well, it has to do with the distance, of course, how far apart they are, right? The further apart they are, the less coulombs that are moving between them, less charge is moving between those 2 points because they're further apart. This tells you how much charge is available, right? There's 2 units of fundamental charge, a proton, electron. So that's something about the charge. This normalizes it, right? It says how much charge is able to be moved through 2 things at a distance r. Right? So once you put all these units together, you get joules out. Right? So it tells you the potential energy of moving 2 units of interaction of 2 units of fundamental charge through the vacuum at a distance r. Okay? Obviously, if we put our atoms material into a different material, E naught would be different. But of course, the space between a proton and electron is just vacuum. And you can't fit air inside that because the components of air are larger than the distance between the proton and electron, so it has to be vacuum. So this is why you have blessing. So that's why we have epsilon naught, right? The only thing that can go between an atom or between a proton and electron is free space, vacuum. There's nothing else that can fit in there. So that's why this number exists. But you can imagine if we had 2 atoms, a positively charged and a negatively charged atom, their net charges would go here. Right? If we had an H plus and an H minus, for instance, we would have, well, these would be +1 and -1. And R is the distance between those 2 atoms, plus and minus atoms. And if these atoms were solvated, for instance, in water, some aqueous solution of some material, then we wouldn't write epsilon naught here because the energy is being transferred through the solvent and not through the vacuum. So the potential energy between 2 ionized atoms inside of water still is 1 over R, but epsilon naught will be different because the permittivity of the solvent is different than the vacuum. It's easier to move charges through a solvent than it is through the vacuum. So the number would be much larger. Okay, so the most important thing I want to take home from this, these are just kind of conceptual things about electricity that I think are important, is that the potential energy of this is only dependent on the distance. It's a one-dimensional object, right? But the fact of the matter is that the hydrogen atom is, as I said, a 3-dimensional object, right? The position of the electron is a 3-dimensional vector, XYZ, but its only potential energy is dependent on the distance between the 2 species. This has nothing to do with angle. Right? I can, as long as r is fixed, I get the same potential energy no matter which way it's pointing. Okay. So here's some interesting results. So let's start thinking about that a little bit more. So the potential energy is spherically symmetric. What does that mean? It means it doesn't matter which angle, which way you're pointing on the sphere, whether you're sitting on the America side of the sphere or the South America side of the sphere, you're in the Australia side, it doesn't matter which part of the hemisphere you are. As long as the distance between you and the center, the proton, is conserved, the energy is the same. Right? And it's only dependent on R. Okay, but we've missed something here. We haven't talked about kinetic energy yet. But kinetic energy is dependent on all three variables, x, y, z. Right? Because if I move, imagine my electron is like this. My shoulder is the proton. My electron's the tip here. This motion is very different than this motion, right? Or this motion. Right? So we have these kinetic, you can think of different angles, right? You can think of different orbits, right? We could process around this vector like this. The electron could go like this, or it can orbit completely around the proton as well, right? We have these stable orbits. We could have these stable orbits. So the kinetic energy is dependent on all three directions. But the important thing is it's also spherically symmetric. Now, what do I mean by that? Right? So what do I mean by that? So what if I do this? Right? So let me just redraw my axis system one more time. What do I mean by it being spherically symmetric? So here's my proton, and here's my electron. Okay, so let's say, for instance, I have the electron on some trajectory around the z-axis, right? What if I have the electron orbit the z-axis like this? Okay. All right, so this has some energy, right? This motion has some kinetic energy. We don't need to calculate it. We can calculate it later, and we will. But let's just say it has some kinetic energy, and that kinetic energy is different, right, than if it goes around the x-axis in the same direction. Well, actually, let's not say that yet. Let's not say that yet. So let's just say that, right? And so this has some kinetic energy, and of course I could come up with another trajectory that starts at the same place that maybe looks a little bit wider, like a bigger precession, right? And this one has a different kinetic energy. All right, so I can convince you that there are multiple ways to effectively move this electron and get different kinetic energies with different x, y, z dependence. Okay, so these have different kinetic energies, but the motion is still spherically symmetric. What do I mean by that? Well, if I rotate this system, by 90 degrees in xz plane, what does that look like? Well, now the x-axis is pointing up, the z-axis is pointing in this direction, and the y-axis hasn't moved. Right? And the electron has also rotated, so the electron is pointing this way. Right? But it's still orbiting, and it's orbiting the z-axis now. So here's my two different possible trajectories orbiting the z-axis, right? So I've moved my system into a different plane, but how can I reproduce these same effects in this new plane? Well, very, very simple. Right? How do I go backwards? Right? How do I realize that these two things are exactly the same? Well, all I need to do is swap z for negative. Swap the x-axis for z and the x-axis, and then swap z for negative x. Right? So what that's going to do is it's going to put the x-axis here and bring the z-axis up this way. All right, so all I have to do, the physics haven't changed. The only difference between this and this motion is I've just changed the labels of the coordinate system. I've just tilted my head this way. Right? All I've done is I've rotated my eyes. Let me write it like this. Right? If this is my eye, like that, then my eye now, in this new rotated form, all I've done is I've rotated my eye this way. Right? All I've done effectively from going from here to here is I've just moved my head like this. Right? So the physics are still the same. Right? So these are spherically symmetric. Right? So the important thing about the hydrogen atom is that it preserves the symmetry of a sphere. Right? A sphere looks the same in all directions. So this preserves. The motion of the electron around proton preserves symmetry of sphere. All directions or point of views look the same. Right? The sphere looks the same in every direction. Okay? And this is true for the physics as well. The physics are symmetric, like a sphere. It doesn't matter which way we rotate the hydrogen atom or the electron, there's always some equivalent way that we can just rotate it back and exhibit it in the same orientation that we want. And so there's some symmetries here. All right, so that's the important thing about. So this is the important thing about the hydrogen atom, right? When we think about the models that we've looked at so far, we've put something in a spherical box, or not spherical box, a square box, one dimension, but we can do it in 3 dimensions. So a square box, and we get these particle in the box wave functions, right? Or we can look at something in a harmonic potential, and we get these harmonic oscillator wave functions. Now we're looking at something that's enclosed in a sphere. Right, so this is a particle in a sphere, if you will. Right, and the thing that creates this spherical behavior is the fact that the potential energy of the system is spherically symmetric. Right? The electron can approach from any direction around the proton and sees the same thing. Right? So the energy, the interaction of the electrostatic interaction is spherically symmetric. Therefore, the hydrogen atom must be spherically symmetric. Right, so you can kind of call hydrogen atom as a particle in a sphere, but of course it's charged. That's the important thing, is that it's charged, which limits our potential to 1 over r. Theoretically, you could have a potential 1 over r squared. You have a potential like that too that's also spherically symmetric, but that doesn't represent charges. It represents something else. So it's going to take us a little bit to get to talking about kinetic energy and potential energy and what the wave functions look like for this system. Okay? And unfortunately, it's going to require a little bit of math, and we're going to have to start thinking about ways to deal with this coordinate system. It's going to be the first challenge we need to deal with. So let me talk about that for a second. So let's go back again. Let me just draw it one more time. Put my proton in the center. And here's my electron at some coordinate x, y, z. Okay, so let's go ahead and just write down very simply our Hamiltonian for this system. And then we're going to realize that we have a problem. So the Hamiltonian is the kinetic energy T plus the potential energy V. And I'll just remind you that this is kinetic and this is potential. All right, and we know what the kinetic energy, right? The kinetic energy looks the same for all these problems in Cartesian space. Looks like minus h bar squared over the mass of the object that's moving, right? The thing that actually has momentum, which is the electron, right? H bar squared over 2me. And now we have to consider its motion in all three directions. So we're going to have the second derivative with respect to x, but we're also going to have it in terms of y and in terms of z. Right, so this is our kinetic energy term here. Okay, so it's the momentum of the particle. Remember, momentum's a vector. So we can always separate the x, the y, and the z components. That's why they're added together here, right? So instead of having just d by dx squared, which is one-dimensional, we have it along all three, which is just the sum. It's the length of the vector, momentum vector. So it's the sum. Okay, and then we have the potential. And we already wrote the potential down. It's a negative term, right? It's always attractive. E squared over 4 pi epsilon naught times r. Well, maybe you can already see what the problem is here, is that we've talked about this thing r, but right, which is the distance between the proton and the electron. This is the potential. Right, so we gotta write r in terms of our coordinates. Well, that's not too hard, right? Because if the vector r is the vector between proton and electron, then the length of r is just the square root of x squared plus y squared plus z squared, right? It's just the length of that vector. X squared plus y squared plus z squared. So we could write this very easily as, if we wanted, e squared over 4 pi epsilon naught x squared plus y squared plus z squared. Right? We could do that. Right? And now we have everything in our coordinates, right? We have everything. Right, we have the momenta, the kinetic energy, the momentum of our particle in xyz space, and our potential in terms of xyz. But this should be scary to you to have this square root of a bunch of squares in the denominator. Let me explain why. The kinetic energy, the component x, y, and z, they're all separate from each other. Right? We sum over the momentum along the x direction, along the y direction, and along the z direction, which is not correlated with my axis system. Right? And they're all separate from each other. Right? The way that the system moves along x kinetically does not affect y or z. They're all separate. Right? But let's look at the potential energy. The potential energy is now a function of all three. Okay, so the problem now is that we have a kinetic energy term that has separable coordinates, x, y, z, and we have a potential where the coordinates aren't separable. All right, so by writing it this way, we've taken the system from a nice separable behavior to one that's inseparable, because the potential is dependent on all three coordinates simultaneously, but the kinetic energy is only dependent on one at a time. So that's a problem. That makes this really, really hard to solve. This makes this problem really hard. So we have to come up with a better way to represent our coordinates, where we don't have these couplings. So we're going to have to appeal, and again, this is the same problem that you come across when you start doing multiple dimensional integrals in Calculus 3. When you start doing spherical integrals and cylindrical integrals, I'm sure your instructor probably told you we could very well do these in Cartesian space, x, y, z, integrate over x, y, z, but it's very hard to do that because you have these square roots and all these different terms and stuff, and you've got to integrate over, you know, spheres and circles and stuff like that. And it's much easier to use angular variables, right? We integrate over angles instead of coordinates, right? You move the polar coordinates, you move the spherical coordinates, and that makes the math much easier. And we're going to find that that's exactly what we need to do here, is that x, y, z is not a very good coordinate system for us because we're spherically symmetric. Our system is dependent, the energy of our system is dependent not on the position of the electron, but rather the distance of the electron. And because the system is spherically symmetric, we can represent its position on the sphere using angles. Right? We can use spherical coordinates instead. So let's do that. And what it's going to do is we're going to have to do a lot of early work getting our Hamiltonian into spherical coordinates. And it's going to make it look really, really scary. But we'll be able to realize that we can break these terms apart into separable terms. So right now, in terms of x, y, and z, our Hamiltonian is coupled. X and y and z all depend on each other. But when we move to spherical coordinates, we'll realize that they're coupled only in r and not in the angles. So what we'll have in spherical, so in this case, we have three coupled coordinates here that all depend on each other. And in spherical coordinates, we'll have two sets of coordinates. We'll have the distance, the r, which is by itself, and it will be completely separable from the angular coordinates, where the electron lies on the sphere at a fixed radius. So we'll be able to separate the problem into angles and distances. And that's going to save us a lot of trouble and a lot of headache. So let me just make that note here, is that x, y, z are all coupled. Right? We want to make our math as easy as possible. Okay, so let's go back and let's come up. Let me just remind you, if you guys don't remember or you've never done it before, let's talk about spherical coordinates. So again, let me write my axis system one more time for you. I'm going to scroll over. Spherical coordinates. All right, so we'll, again, remember we're going to implicitly define our origin to be our proton. And I won't label it from here on out. And we're going to say our electron is some point in position space x, y, z. Okay. Right? And we want to come up with a new set of coordinates that describe this position without using x, y, z. Right? And we know one of the coordinates is going to be r. Right? We want to define our electron in terms of its radial coordinate. But then we have to determine where that radius, that vector, is pointing in space, right? What's the latitude and longitude, if you will, of the object? So we introduce two angles. First is the angle theta, which is the angle subtended between the position vector and the z-axis. And then let me see if I can draw this a little bit easier. Just a sec. And then there's going to be an angle that determines it. I'm sorry, I have this oriented wrong. Phi. Okay. Which is called the azimuthal angle, or sorry, I forget what this is called, but there's two angles, right? So the angle theta determines how far away we are from the z-axis, and phi tells us which way it's pointing along the xy point. So let's just look at that a little more carefully. All right, so what are our conversion factors? So r, of course, we have already calculated what it is. It's just the square root of x squared plus y squared plus z squared. And what values can r take? Well, the shortest distance for a distance is 0, right? It can't be any shorter than 0. And what's the longest it can be? Well, it can be as long as it wants. So it's bounded by above by infinity, right? So r can take any value between 0 and infinity. Theta. Well, what is theta? Well, theta tells you something about how much the vector goes up along the z-axis. So it's going to be related to r and z. Right? And that's going to be from angle. That's going to be far over hypotenuse. Sorry, near over hypotenuse. So theta is the inverse cosine of z over r. And what can theta run between? Well, it needs to specify how it's pointing with respect to z. So what are the only unique values? Well, either it's pointing straight up or straight down or anywhere in between. So that's 180 degrees of rotation. So theta can be between 0 and pi. Okay, and phi. Not hard to calculate. It's the inverse tangent of y over x, right? It tells you the angle in the xy plane. And basically it could be anywhere in the xy plane, so it has 2 pi phase, right? There's 2 pi radians to choose from, so it can be anywhere between 0 and 2 pi. Okay. So let's talk very, very simply about how this breaks up. Remember that our potential is only dependent on r. Okay, so now our potential just goes down to one function, right? It's just 1 over r. Right? It's the length. So we're going to parameterize the system by the length, or its distance from the proton. We don't have to worry about x, y, z anymore. And remember, because it's spherically symmetric, the potential has no relationship to theta and phi. It does not matter which way r is pointing. It just matters the length, right? So now our potential is completely decoupled. Our potential now has to do with just r. Okay? But we have to worry about the kinetic energy now. When we talk about the kinetic energy of this particle moving, we're going to have to consider again how it's moving in around the circle, right? How does theta and phi change? But also does the system also move in this way as well? Right? Does it get closer or further away from the proton? Right? So the kinetic energy is dependent on all 3 parameters. But the amazing thing is because the energy is spherically symmetric, because the atom is spherically symmetric, the kinetic energy relationship between the angles in r, there is none. They're decoupled from each other. So the kinetic energy as a function of r has no dependence on theta and phi and vice versa. So r and the angles are coupled to each other, as we'll see. But r is completely decoupled from theta and phi. Okay, so what we'll be able to do is we'll be able to solve the r problem and the angular problem separately. We'll see that in just a second. Okay. That's going to make things really easy because now we don't have to worry about the coordinates along all 3 dimensions. We can worry just about the r problem, and we can just worry about the angular problem separately because they're not related to each other. They're independent of each other. They're decoupled. So let me just write down. So once you solve these for x, y, I just want to write down the conversion factors because they'll be useful. X is equal to r cosine phi sine theta. Y is equal to r sine phi sine theta. And z is equal to r cosine theta. Okay, so these are our conversions. Okay. We won't have to do that many of these conversions, but it's nice to have them written down because eventually we're going to have to take integrals of our wave functions, and we're going to want to think about how to convert from our integrals from x, y, z into spherical coordinates. Okay, so now we have this new set of coordinates, and I promise you that they're going to make our life easier when we go down the line once we do some work. I want to make a really, really quick comment that's very helpful, and we'll see this over and over again in this class, is that I'm just going to jump ahead just a little bit because I think it's a really important consequence of spherical coordinates. Eventually, we will write wave functions, hydrogen wave functions, that look like functions of r, theta, and phi. Right? Our wave functions are going to be functions of these three coordinates. Right? And we're going to want to remember when we integrate these, right, we're going to have to, in order to calculate properties of our hydrogen atom, we're going to have to integrate these wave functions, right? So in 3D, we will have, for instance, that the average value of some operator is going to be an integral, initially, of our wave function xyz times our operator times wave function dx, dy, dz. Right? So if we were to write these things down xyz, this is what it would look like. And what would the bounds be for our wave function in xyz space? Well, it would just be 0 to infinity along all of the axes, right? Because the electron can be anywhere except for at the proton, right? It can be anywhere except for, no, sorry, that's wrong. I apologize. That's wrong. Negative infinity. Right? So this is what the integrals would look like in xyz space. So what would they look like in spherical coordinates instead? Right? Because in order to do that, we need to do u substitution, right? We need to substitute the x, y, and z for r, theta, and phi. And we also have to change the dx to dy and the dz for r, theta, and phi, right? We have to calculate dr in terms of dx and dy and dz. Right? So when I convert to spherical coordinates, again, I still have three integrals, but now r psi is a function of r, theta, and phi. And I want to highlight two particular regions of this integral that change. It's the bounds and the volume element, the differential element, the dx. Right? And when you convert dx, dy, and dz into spherical coordinates, you get an additional conversion factor from the u substitution. And I'll write it down here very clearly. You get r squared sine theta. And then you get dr, d phi, d theta, however you want to write them. Right? So every time, so this is an important, right? So I'll just write this out, and that dx, dy, dz is the same as r squared sine theta, dr, d theta, d phi. Right? This conversion is always there. So anytime you're going to do integrals in 3 dimensions and spherical coordinates, you always have this r squared sine theta conversion factor. Okay? We can derive this if you're not convinced of it, but this is always there. You probably did it in calculus. Right? So we have this additional factor that's always in the integral. All right, and so how do our bounds change now? Well, our bounds for our coordinates are no longer negative infinity to infinity, right? They're angles and distances. Right? So dr, let me just highlight each of these in color so that it's not confusing which one is which. So the d theta is on the outside. That goes from 0 to pi. D phi goes from 0 to 2 pi. And r, which I have in red, runs from 0 to infinity. Okay, so anytime we're doing 3-dimensional integrals in an atom, we're looking at three-dimensional objects, and we put it in spherical coordinates, our integral is always going to look like this instead. It's going to have r squared sine theta, and we integrate with these bounds always. Right? This is all space in a sphere. It's all possible radii and all possible angles. Right? Integrating over a sphere. You always get this vector of r squared sine theta on the top. Okay? I like to write this now. We're going to see it every time we do an integral. It's going to show up, but it's nice to talk about why these things appear. Okay? And I won't derive it, but it's pretty straightforward. All you have to do is do u substitution for x, y, and z into r, theta, and phi, and you get this r squared sine theta out, and you do u substitution. We won't worry about that. It's just a bunch of algebra. Okay, so again, the thing I want to take out is I'm just building tools up here. Is that we're jumping ahead a little bit because we haven't even defined what these integrals look like, what these wave functions look like, how we're going to solve the Schrodinger equation for them, or any of that. But I think it's important that we talk about the tools, right? We got to at least set up the problem that we need to solve and understand how to do it. And so from here on out, when we talk about atoms, we're going to talk about things in spherical coordinates, right? We're not going to talk about the electron's exact position. We're going to think about it in terms of its angle, in terms of its distance. Right? One way to think about this, and this is the way that Niels Bohr thought about it, is that the distance tells you something about the distance. Think of it as the proton being the sun and the electron being a planet, right? That you have these orbits, right? And what does an orbit have? Well, it has some angular behavior, but it also has a distance, right? The distance between the two objects. And what Niels Bohr said about what he proposed for a hydrogen atom is that you have these unique discrete orbits that have different r's. Right? You can have an orbit that's the fundamental orbit, that's where the electron is as close as possible to the electron, right? We call that the ground state. Right? And there's orbits that are quantized that are slightly larger, and they're quantized by some integer, just like every other system, that are different r's, and they have different angular behavior as a function of r. And it turns out that he's right. You can interpret it this way. You get the wrong answer from his interpretation. Like that idea of stable orbits, that Bohr model of the atom that you guys are so used to seeing, right? The idea of having, and I'm sure you guys have seen it before. The classic picture of an atom, right? Drawing of an atom where you have a nucleus and you have these orbits that look like this. Right, and you have these orbits that look like this around it. That's not the best picture of the atomic. Right, this is what people talk about. This is what's called the Bohr model. Right, you have these unique orbits that have unique distances. They're quantized and they have different angular behavior depending on the distance. This kind of gets you to the right answer for hydrogen, but it doesn't get you the right answer for any other atoms. And in fact, there's things about hydrogen this gets wrong, as we'll see. Okay, so this gets you in the right idea. The idea is that the way the system is going to quantize is we're going to have unique orbits that have unique average lengths and angular behaviors, and there's different orbits of different energies. And obviously, the closer the electron is to the atom, the lower the energy that orbit is, because the potential is attractive. Right? The energy is lower the closer the electron is to the proton. So there's some set of stable orbits that you can have, or that's what Bohr says, of the electron around this atom, and that's what we're going to look at. But we're going to realize they're not really stable orbits. So that's a bad way to look at things, because it actually predicts the wrong answer. But it's hard to see that just yet. Right? So what we're going to do is we're going to tackle this problem this way, just like Bohr thinks. Let's think about it in terms of orbits. Right? Think about it about an object rotating around another object at some momentum. And then we'll take that physics and apply it to our problem on top of the fact that we're dealing with this potential difference. Right? So we have this electrostatic, which is dependent on r, and we also have some sort of orbiting thing that's dependent on the angle at fixed r, these orbits. Okay? So we're going to have to deal with these two things separately. We're going to have to think about how does the energy change, how does the hydrogen change as a function of distance, and then at fixed distance, how many stable orbits are there, and what do they look like? Okay, so we're going to separate it into an angular problem and a radial problem. And I want to focus on the angular problem this week, for the next 5 minutes. I'll set it up, and we'll come back to it next class. Once we understand the angular problem, which, by the way, is incredibly ubiquitous in chemistry, we're going to learn the concept of dealing with things, the quantum mechanics of angular motion. Very, very fundamental to chemistry and physics in general. It's going to immediately bring us to a theory that allows us to explain the spin of an electron or a proton, which is something I haven't even mentioned yet. We're going to understand the angular problem, and then we can go and tackle the radial problem. And when we combine these two things together, we understand at a fixed radius how an electron orbits angularly, then we can understand how it works as a function of radius, then we know the whole system. Right? So it's going to be a two problem part. We're going to tackle the angular part where we're going to understand angular momentum, and then we're going to tackle the radial part, which is the electrostatic. And these two techniques, the angular part turns out to be the most interesting part of the whole problem. All right, the techniques that we're going to learn from understanding the motion of angles and the motion of movement in a circle, angular momentum, turns out to be extremely, extremely important in just about everything. Okay. So we don't have enough time to get to complete angular minimum, but let's just set the problem up and start thinking about it today. So what I want to think about today is we're going to first start. So first thing we're going to do is solve the angular problem. All right, so what we're going to do is we're going to fix the distance between the two objects that are rotating, right? Our two proton and electron, if you will. All right, so what we're going to look at is what's called the rigid rotor problem, the rigid rotor model. Okay, and in fact we're going to appeal to chemistry a little bit to understand this theory, because I think it's easier to understand in terms of molecules. And then we'll realize that this methodology applies directly to the hydrogen atom. But the idea is very simple. We're going to have two bodies. Just like we did for the harmonic oscillator, we're going to have two bodies. That are separated we're going to separate them by a distance r, right? The bond length, or at some distance. I don't want to think about bonds just yet, and we have two masses, right? There are two masses, M1 and M2. Okay? And just like we did for the harmonic oscillator, we can define a center of mass. Right? So there's our center of mass here. And what I want to think about is the motion, the physics of taking this system and rotating it around the center of mass. Okay, so we're not stretching the bond anymore, but what we're going to do is think about this as a figure skater with its arms open. Center of mass is right here in the middle of the chest for a figure skater, and these are the two. You can imagine the figure skater's got one weight in one hand and another weight in the other hand, M1 and M2. And we want to think about the angular momentum, or the energy required to spin this molecule or this figure skater at some velocity. Right? How much energy does it take to spin it at some rate? Okay, so what we want to do now is we want to take each of these atoms. We want to fix r. So we want r to be fixed. So fixed distance r. And we're going to rotate these atoms. We're going to rotate the system collectively. Right, so M1 will rotate like this, and M2 will rotate in a smaller around the center of mass in the same direction. All right, so we're going to rotate object about center of mass. Okay. All right, you can think of this as a diatomic molecule. You can also think of it as a proton and electron. It doesn't matter. Okay? However you want to think about it. Okay, so what does physics say about this system? All right, so we just go peel back to introductory physics. We've got about 5 minutes left, right? So we want to define what's called just like we did for linear motion, we define the momentum. So we need to define the angular momentum of this system. Right, and angular momentum is a vector, L. And there's a couple different ways to write it. But one way to write it is I times omega, where what I is called the moment of inertia. And omega is the angular frequency. That's how fast we're rotating the system. All right, so if we want to spin our figure skater so that it completes a whole rotation in 1 second, the angular frequency of that would be, that would be 2 pi radians in 1 second. So the angular frequency would be 1 over 2 pi. Right? It's how many radians per second. Or sorry. So if you want to rotate 2 pi in 1 second, then the angular frequency is 2 pi. 2 pi. Right? So this is how fast. So this is the number of radians subtended per second. Right? So that would mean that if 1 full revolution in 1 second, that means 2 pi radians a second, which means that omega is 2 pi per second. And what is the moment of inertia? Well, the moment of inertia tells you something about how the mass is distributed in your rotating object. Okay, so it's a number. And it has to do something with the masses and the distance separated by the masses. And in fact, for a two-body system, we can write it down exactly. For a two-body system, like we have here, I, the moment of inertia, is equal to the reduced mass times the distance squared, which is, again, m1, m2 over m1 plus m2 times r squared. Okay, so the angular momentum of our object and how much momentum we create by spinning this object has to do with the velocity at which we spin it, an angle. Right? You can think of this as a velocity times something that looks like mass. Right? I is mass times the distance squared of the mass. Right? So it tells you I kind of tells you some sort of effective mass distribution. Right? How does the mass exist in space along the thing that's rotating? And we're going to rotate that mass, m, times some velocity and angle, v. Right? So this kind of looks like m times v, which is momentum. Right? But now it's angles. Right? Instead of moving something linearly through space, that would be m times v, we're holding the object in space, we're fixing the center of mass, and we're rotating it around the center of mass. Okay? So you still have a momentum, but the momentum is now dependent on how fast you're spinning it, how fast does it subtend an entire circle. Right? That's the velocity, if you will, the angular frequency. And the rate and the mass term is this moment of inertia, we call it. And again, it has something to do with the masses of the two objects. Now, in the case of our electron and our proton, the mass of the proton is 1,000 times the mass of the electron. So this number looks a lot like 1 over the mass of the proton. The electron's size is very, very tiny compared to the proton. The proton really determines the moment of inertia for this. All right, so we'll have to think about that a little bit. But what we'll find is that when we think about this very general idea, spinning a diatomic molecule, the physics that we come up with the angular momentum of this will be directly applicable to the electron. Directly applicable. Everything that we'll learn from this can be directly applied. Okay, so this is the angular minimum. And of course, what we want to do is we want to relate this to energy, right? I want to know how much energy it takes to get this thing to spin up to a certain rate. Well, it turns out that's super easy to calculate, and this will be a really, really helpful relationship for us, is that the resultant kinetic energy, so I'll put this up here. So if the angular minimum of the system is I omega, then the kinetic energy, T, turns out to be L squared over 2I. Which is, well, let's look at that. That's going to be equal to 1/2 I squared I omega squared. Right? Doesn't that look a lot like kinetic energy? Right? We have kinetic energy is equal to 1/2 times the mass times the velocity squared. Right? It's the same exact thing as regular kinetic energy, except now we're doing it in a circle instead. Right? So all the math works out all the same. All the units and all the evaluations are the same. It's just that we've rescaled our problem from translational motion to rotational motion. But the kinetic energy is still 1/2 mv squared. It's just everything looks a little funky. We have omegas and i's now. Right? Okay, so we'll stop here. I'm out of time. But right, I've already written down a new formula for kinetic energy that we can then apply to our Hamiltonian. Right? I don't have to think about dx squared, dy squared, all these derivatives in terms of position. I now think about things rotating at an angle with some effective mass. All right, so we'll be able to relate this t to the angles of motion, and then we'll get up a new Hamiltonian that will allow us to describe the motion in terms of the angles instead of the positions. Okay? That's going to be our goal next class. All right, guys, homework. Get your homework in if you haven't yet. Exam will be out after class on Wednesday. Have a good one.